Hi, good morning, everybody. This talk was actually titled Next Gen PaaS Architecture. At the time, I think we haven't announced the availability of this technology to external developers, and that's why I think it was called Next Gen PaaS Architecture. But the technology that actually represents the Next Gen PaaS is what I mentioned here, which is Microsoft Azure Service Fabric. Today, I'm really excited to talk about this Microsoft Azure Service Fabric. I'm Gopal Kakiwaya. I'm a corporate vice president at Microsoft. I have, for a great part of my career at Microsoft, I really worked on this technology for more than a decade. I conceived, incubated, realized, and productized this technology. We really built this technology for use by the first-party services. We saw our first-party services trying to solve the same hard distributed systems problems many, many times. And we thought it would be better if all of them leveraged or built on top of a common distributed system substrate so that, the learnings and the bug fixes that happen in one service will benefit other services as well. With that in mind, we built this technology. It has been in production at Microsoft for more than 5 years. Many first-party services are built on top of this, and we felt that time has come for us to really make it available to other external customers as well, so that you guys can build similar applications and services on top of this. That brings us to this moment in some sense in that this technology now is available to you. You can actually go to Microsoft Download Center and download the SDK. Using Service Fabric SDK, you can actually set up a real scale minimized cluster on your development boxes and build scalable, reliable applications. The same applications that you build on the development box can actually be transferred as is to run on Azure when we make this technology available to you guys as a Azure hosted offering in the next couple of months, and also actually run them on premises because we are going to ship this technology as part of the upcoming Windows Server 2016 release. So this technology gives you the portability that you're looking for, the hybrid aspects, and this is the agenda of my talk. I'm first basically going to talk about how the application development has changed in the cloud world and how Service Fabric helps you with building cloud-native applications. I'll talk a little bit about how one can build scalable, reliable, easily managed microservices using this technology, and take a little bit of a peek under the hood of how this technology has been put together, the role of major subsystems that power this technology and the problems they solve with some demos, and then finally, conclude with a summary. Not long ago, our life as developers was simple. We had 8 to 5 jobs. We wrote a bunch of code every day and shipped those features every 2 years in a box product, and then the cycle began. Along came the cloud and everything changed for us. Not only are we responsible for building features, service-specific features or application-specific features, we are also now responsible for making sure that the code we write is scalable, infinitely scalable. It needs to start small, and in some cases, if your application or service becomes popular, it needs to scale to large, very large scale. We are also responsible for making sure that our code runs reliably, is always available. And we are also responsible for making sure that our code runs efficiently. I mean, efficiently in the sense of it has the best performance, lowest latency, or has best COGS, and COGS means cost. We also became responsible for data sovereignty and data continuity issues. So suddenly, I think we have been asked to go and deal with all these problems, but our core job is still, developing features that are specific to our service or our application. Would it not be nice for us to have a platform that takes care of a whole bunch of things that I listed on the right side of this slide, so that we can go back to focusing on solving the service-specific problems, or develop the features that actually help the business, and we can deliver them faster. That's how this technology came into existence. The same journey was actually, our first-party services went through the same journey, and out of that came this technology. Similarly, the architecture that we are so used to in building services or applications has changed in the cloud world. We are so used to building three-tiered architectures. We use the same languages, same tools, and processes to go and develop all the tiers. We actually go and, because of that, generally these tiers are tightly coupled. So we generally take maintenance windows like over the weekend, so that we can go and patch and upgrade all the tiers together in one shot, and make the service come back up alive the following Monday. But that's no longer acceptable in the cloud world. So you have to really think about how do you design your and architect your service or application so that you never take downtime. Similarly, we are so used to building reliability, in the three-tier world, by depending on hardware. We always use smart, big iron boxes, SANs, and other things to achieve reliability in our services. But in the cloud world, no such software. We want to use the opposite. We want to use smart software, build reliability, unprecedented reliability, by using smart software and smart platforms to build our services and applications. So this brought us to the modern architecture, and most of the cloud services, if you go and take a peek under the hood of any one of Microsoft services, or for that matter, any third-party services out there, you would actually see that they are all built as out of small pieces of loosely coupled components, are what we call microservices. And again, it would be nice if the platform underneath actually provided us with the capabilities that are necessary for building these microservices, and that's where, once again, this technology comes into play. When you're building any internet scale service, or any interesting service for that matter, you really have to think about three things, and we have definitely at Microsoft think about these three things deeply when we are building any of our services. The three things are scale, reliability, and cost. We really need to think about scale systematically from the get-go, because scale is unpredictable. You need to have the same piece of code run at small scale, on premises in some cases, and as the scale and as the popularity of the service improves, it may need to scale to a very large scale. And you do not have to go back and revisit the architecture. You really want to design it with the right tenants in the mind, the scalability tenant in the mind. So that's where the scale point comes in. The second point is reliability. Once again, you can no longer afford to take downtimes. We are living in the 24/7 world. Everything is connected, cloud first and mobile first world. And there are no maintenance windows, for you to really go and, take down your service and then, bring it back the following Monday or the next morning. So the service has to remain always up and running. And reliability has to be obtained by thinking about that. You can only achieve reliability by thinking about it more systematically. You need to run on commodity hardware, because in commodity hardware, failures are going to be common. We have seen lots of failures happen in our system, and many bad things happen to us. Things which we think are once in a blue moon events do happen when you're running at a very, very large scale. When you have millions of machines in the data center. And finally, you have to really think about the cost. You really cannot afford in the modern world. Actually, when you reach a certain point in scale spectrum, in fact, smart hardware doesn't help you at all. But maybe up to a point, you really can have, gain a bunch of reliability by running on, big iron boxes, SANs, and things like that. But at some point, that tenant will break down, and you really have to think deeply about how you architect your service so that it can run on commodity hardware and leverage smart software for achieving reliability, as well as the cost efficiency that you really have to achieve. Again, this goes back to our life as developers. As developers, we never thought about the cost of running our software. We always built our software thinking that the box never, the machine on which the software is running never dies. But that's not true. It dies all the time. So how do you build your software without actually you thinking about the machine failures? And that's where technologies like this come into play. So if you are thinking about these three problems, then a whole bunch of distributed systems problems come right, stare at you. Here, like for example, how do you deal with failures in the system? How do you do failovers? How do you do replication? How do you deal with state? How do you do placement? How do you do orchestration of upgrades? The lifecycle management of your application. And this is where this platform has solved these problems. Each one of these problems individually takes years to build, and in some cases, by the time you realize that you have fully built it, many other problems will come and stare at you. For example, you think that you solved the failover problem or failure detection problem. Then you say, now I can assume that my code is running reliably. But what happens if I need to patch and upgrade my code? Then that problem you have to solve. So if you actually put all these distributed systems problems together, you actually can see that there is a comprehensive distributed systems platform that one needs for building these kinds of services where all these problems are systematically solved for you. And that's where Service Fabric comes into play. Using Service Fabric, you can actually build scalable, reliable, easily managed services, and you can deploy them on premises. Using when we ship as part of the server, you can actually deploy them on Azure, or for that matter, you can even deploy them in third-party, your favorite clouds. Not only are we going to ship this technology as part of server, but we are also going to make it available on Linux. And we are going to expose these APIs in other languages and frameworks like Java and JavaScript. So using this technology, I think you can still continue to use your favorite framework and run on your favorite OS and run it anywhere and anytime you want. And that's a promise I think we are making with respect to this technology. This is all good, it's all great, but then did we actually just build this technology like last year and then giving it to you? No, that's not the case. This technology, as I said, that we conceived this technology more than a decade ago, and it actually powers all of these services at very, very large scale and has been in production for 5 years. The core of this system has been baked for a very, very long time. In fact, technologies like these are considered secret sauces for many cloud companies, and that's what we are actually now making available to you. More importantly, we are not giving you guys a different version of the code we run. We are actually giving you the exact same code that we actually use underneath each of these services. For example, if this code does not work, if Service Fabric does not work, a whole bunch of core Azure infrastructure will go down. This is the Service Fabric is the one which is managing 1.4 million transactionally consistent databases running on tens of thousands of machines in Azure as we speak. It is the technology that powers a whole bunch of consumer-grade, user-facing services like Cortana, which actually span multiple data centers. And recently, they had an outage of an entire data center, and the service continued to run. So this is the technology that we had internally. We built it initially for internal needs. And then we realized that, hey, first party equals third party. And that's how we said, now that we have actually gone through the pain of actually understanding what needs to be built and how it needs to be built and how it can be leveraged, we are now making available to you guys this this cake or this platform so that you guys can also benefit from similar, get the similar benefits. I will talk about what parts of the system are fairly new at the end of my talk, but you can assume that the cake is fairly well baked at this point of time. And this is the technology you can actually take a dependency on, because I'm not saying this lightly in the sense that I have an obligation to make sure that anything that is built on top of this technology actually is built, built right and survives failures and all those tenets that I described in the past: scale, reliability, and easy manageability. So, in this, that basically is an intro to why we really need a technology like this. And I'm now going to take a little bit of a peek inside to really talk about how this technology is put together, the major subsystems inside this technology, the role they play, and the problems they solve, and actually demonstrate the problems showcase the problems they solve using a set of demos, which with my colleague here. So I think this is a very important point to get across. What exactly is a microservice? We keep hearing about this term, and we also keep hearing about the terms called containers and other things. So I want to spend a little more time on what we mean by a microservice. If you are asked, or if I am asked today, how do go and build this internet scale service? It may be a particular, it may be a problem that needs to be solved in a particular domain, and we are asked to go and build a service that solves that particular problem. So the way I would think about the problem, and the way I think you guys would, I expect to think about the problem, is not to think about the number of machines or what should I do on a machine. You really think about your problem. You decompose that problem into individual components which are loosely coupled, and you actually will want those components to interact with one another and solve the problem that you're looking for at the service level. You never think about machines. If you actually, many times you keep hearing about, a cloud, and then I can get this many machines, I can use this service, or I can, I can put together these things together. But you have to think hard about what is it that is happening underneath the service that you're trying to use. Maybe, like for example, Azure databases. How is Azure database itself has been put together? Those guys also did not think about their number of machines. They think about, hey, what is it that I want to solve? The problem I want to solve is the database problem. How do I make databases available on demand? Whenever you want a database, we need to have one created for you. And we need to make that database available all the time. And what are the constituent pieces that I need to make an offering called database as a service? And so you start with that problem and think about the different components of that particular service. In the case of database as a service, in the case of Azure DB, there are a whole bunch of services underneath this, what I call the microservices. Like there is obviously the most important microservice called the database. Then there is a microservice in front of it called protocol gateway, which is terminating the tedious connections. Then there is another microservice which is responsible for providing the management operations that are necessary. For example, whenever you go into an Azure database, in Azure, and ask for a database, it is this protocol, the management endpoint that is receiving that request and actually calling Service Fabric, create microservice for me, API. So there's a whole bunch of, there are 7 or 8 services which are running underneath, Azure database service. So a microservice is nothing but a piece of code and its associated state. That you think, you are writing code, you think about, what you're doing, what is the state that you're maintaining, and that's all you should really think about. You should not think about machines, or for that matter, even if you think about the machines, you're not going to, be able to solve your problem effectively. So, and these entities are what we call microservices, interact with one another over well-defined protocols. And whenever you are thinking in your, about solving the problem for your service, you think about, hey, where is my microservice running? You never think about what exact machine in which that microservice is running. So you always resolve the endpoint at which a microservice is running. For example, the tedious protocol gateway, which is terminating the tedious connections in Azure DB, When it actually receives a request to connect to a database, it's not actually asking, hey, which machine is this particular database is running? It's asking, which endpoint should I connect to? So the machine layers are completely invisible when you're working at the microservices level. And more importantly, you should be able to really reason about your system by thinking about these microservices as always remaining consistent. I mean, in the case of stateless, I'll talk about the two types of services, but it is important for you to really think about the fact that a bunch of failures have happened, the fact that a bunch of upgrades have happened should not affect the consistency of a service. The database should remain transactionally consistent. The data that you committed with the transaction needs to be available when the even if a bunch of failures have happened, a bunch of upgrades have happened. For example, SQL undergoes 5 upgrades roughly for their service. Different pieces of that service get upgraded at different rates. That's another one of those things with the advantages of microservices. When you're building microservices, you do not go and upgrade all of them. You can upgrade them individually. It allows you that agility, the developer agility that is necessary for you to go and solve a set of problems that are specific to a given microservice and upgrade that without having to worry about upgrading everything. And then the system takes care of these upgrades, making sure that you never lose availability of the running service, even though this upgrade is happening underneath that service. This is an important distinction, and I think the two types of services that people talk about are stateless microservices and stateful microservices. Obviously, I think many of us are familiar with what we mean by stateless. Stateless basically means that the service or the microservice does not maintain any state between the request and its response. Sorry, outside of its request and response. So, like protocol gateways are a classic example of stateless microservices. Azure Cloud Services, in the current incarnation of Azure Cloud Services are also essentially stateless because they can be shot at any given point, and the system is supposed to survive. Web frontends, all the pages and all the things, even in 3-tier architecture, the web is always considered a stateless thing. And many people talk about how you build scalable services by making sure that you can build a whole bunch of instances of stateless microservices. In the case of webs, you create a bunch of front ends, and in the case of protocol gateways, you maintain n instances. So the way we achieve scalability for stateless services is very simple. You maintain n copies of that stateless service, and to an extent, it's a simpler problem than the next one. But I mean, there is a hard distributed systems problem here, but in general, this is how we think about the world. But then comes the stateful part, which is the hard part. This is the stateful microservices. Here is where, as we traditional enterprise developers have thought about, state is hard, so I'm going to depend on a database, or I'm going to depend on a SAN, because I do not know how to solve that problem by creating n copies of my code. But somebody has to solve that problem. For example, Azure Database, which itself is a stateful stateful service, needs these problems solved for them, and that's what we did. We solved these problems. So stateful microservice is the hard microservice to get it right. So the way you achieve reliability with stateful microservices is by maintaining n copies of that state and ensuring that those n copies of the state remain consistent. In other words, whenever you can go to any copy and you can get the answer that you're looking for, irrespective of the copy that you went to. In other words, these copies cannot diverge. And that's where I think the hard problem arises in distributed systems. And once again, this is the technology that allows you to build these stateful and stateless microservices. And many times you go across and you see people talking about how you achieve scalability by making everything stateless. That's true, but up to a point, because if the entire world is stateless, it isn't an interesting world. You have to have some state. There has to be some kernels of truth somewhere maintained in the system. And who is maintaining that kernel of truth? Kernel of state. And that's where these technologies come in. And you will realize that it is not that hard for you guys to really go and build stateful microservices because we do a whole bunch of heavy lifting. And that's what I'm going to focus in as a set of demos, as well as showcase how the system comes together in building these kinds of services for you. With that, I'm going to we're going to showcase the problem that needs to be solved for stateless microservice. In this particular case, Vipul, I'm going to ask Vipul to come and talk about a stateless microservice. In this particular case, we are using a visual object, which is actually freely moving in space. It has state inside it. The state it has inside it is, its location and its, past 10 locations. You can see the tail of that guy actually as it's moving around. And let's assume that it is a stateless service. We built it as a bunch of code. We basically fire a timer every few seconds. We move the thing, and then we update the location, and then we move on. Now we build this code. I will also show you guys the code as the talk progresses. And let's assume that the machine fails. What happens? I think that's the problem that this demo will show.
Hi guys, I'm Vipul Modi. I'm one of the engineering manager working on the Service Fabric team. So as Gopal described, this stateless microservice is running on my local cluster. It's a 9-node cluster, and this runs the exact same code as Gopal mentioned that you will run in production. On my development box, I have basically 9 nodes. In production, one machine is going to have 1 node of Service Fabric running on top of it. Right? So here is the microservices application. It has a bunch of microservices inside of it. We are first going to focus on this stateless microservice that you see here, which is the visual object stateless service. It has 1 copy of it, which is running on node 6. So let me refresh, make sure it is still running on node 6. This one, yes, it is running on node 6. So what I'm going to do is to basically fail node 6, to say, hey, I'm going to shut down node 6. So you can think of this as a failure that's happening in a data center when a machine goes down. Watch what happens to the object, and I'm going to put this one to refresh as well. And so let me refresh everything here. And stateless service, partition. Okay, this one is the right one. And I'm going to stop the node 6.
And see, it actually stopped because it died, and then it started somewhere else. And you can see that it must have moved to a different machine.
Okay, so let's see. Let me refresh, and you can see that it moved to node 3.
So think of what happened in the system. There are a bunch of there's a stateless microservice that was running on node 6. We just maybe because of machine failure, that machine died. The system detected that this machine has died and moved a copy of that code to run somewhere else. Obviously, because we lost state, because it is stateless service, it started from somewhere else in the system. So basically, this is how, if you actually think about Azure DB, if you go and think about the protocol gateways, whenever you actually have a protocol session, when the TDS protocol session in databases, when you open a TDS connection or a SQL database connection, that connection gets terminated at a front end, and if that front end dies, a different front end comes into play and then takes over. So this is how these stateless services are made reliable. So we always ensure that if you say, I want n copies of my stateless microservice running, we will keep and guarantee to you that in this particular case, the request to the system is to keep 1 copy of it running, and you can see that we already promised, we kept our promise. So this is the case for stateless microservice. And what are the subsystems that came into play to provide you that guarantee? And that's where these 2 layers come in. The 2 layers I'm going to talk about next to actually detect failures in the system are the transport subsystem and the federation subsystem. The transport, obviously, in any distributed systems, you have to have machines be able to talk to one another. So transport subsystem is the place where we actually have machines talking to one another because we have this efficient, transport or communications system where machines can exchange a bunch of messages, and the system actually does its best to deliver the message. I want to emphasize the word best. It doesn't guarantee that a message always gets through. And there is no way you can actually guarantee if you're running on commodity communication networks. Remember, the data center networks are not that hardened sands and other things. They die all the time. So basically, this system, federation, the transport, in the case of transport, it is doing its best to deliver the message. We have a bunch of security, encryption, all the kinds of things that we are all familiar with in enterprises with respect to making sure that it's called enterprise-grade security. So we support Kerberos, we support certificates to make sure that the cluster that is set up by the service fabric is secure. Nobody can tamper with it. Nobody can go and mess with it unless they are authorized. So that's the stuff that happens in the transport level. Above that is the federation. And I want to motivate the role played by the federation in the next few slides by actually talking about what happens in a typical data center. When you go to a typical data center, and you ask for a bunch of machines, you get a bunch of machines. You go and ask Azure, or for that matter, any other cloud, hey, I want 10 VMs. You get 10 VMs. What do you do after that? Again, think about what I said. You're trying to solve a problem of building service or an application that solves a particular problem in your problem domain. But you start with machines. You have not thought about how to decompose your problem. That's how you thought. I thought, hey, I have my problem. I want to decompose it into a set of microservices, and I want them to be built. I don't want to think about machines, but you get a bunch of machines. And you start with what happens if this machine fails. If you don't have service fabric, that's what you're facing. What happens if this machine fails? What happens, who is part of the cluster? How many machines did I ask? Do I have 6? Do I have 3? Do I have 2? You do not know the answers because the answer you give at this moment is different from the answer you would give at the next moment. And how is the system supposed to react with it? And who is solving this problem for you? And I think that's where the federation subsystem of Service Fabric comes into play. It basically creates the cluster, what we call the cluster, so that now the Service Fabric federation layer can tell you, hey, this machine has failed. These machines are part of the cluster, and it does that by not doing a lookup of some site table or because the system is extremely dynamic. When you have 10,000 machines, I'm only showing you, for the sake of clarity, 6 machines, right? But in reality, in the case of Azure databases, there are thousands of machines in these clusters, and the way it actually determines whether a machine has failed or whether what machines are part of the cluster is not by actually doing some database lookup. It does it by actually following a bunch of hardcore distributed systems protocols internally within the system to answer those questions. In other words, there is no database when this system is coming up because the database itself is built on top of it. That's another way to think about this problem. Who is solving this problem when the world doesn't exist? The system has to be self-sufficient. It needs to come up on its own. It needs to answer these questions on its own. And that's what this system is trying to solve at this layer. So the way, the system, a little bit of a peek into how the system works, the federation works. In Service Fabric, every machine is given an identity. It has a number. When you have a number, there's a natural neighborhood around that number. And that's what this particular slide is trying to show, is that at time t0, machine 64 has its neighbors 83, 76, 50, and 46. And at time t1, a few things are happening. Node 76 and 64 failed, and node 61 arrived. Remember, Vipul had showed to you guys a real scale minimized cluster running on your development boxes. That's why we give you this promise that the code that you write on your boxes runs, more or less as is in real deployments, because that's how you develop your code. You can do your FI debugging. You can, and there's a bunch of sessions after this talk where you can go and actually understand how do I build this microservice. I'm only focusing mostly on the motivational aspects of why you need to care about building microservices and how you can build those microservices. And then there's a bunch of follow-on talks where you can actually go and understand how do I write the code for these things. But I'm, at time T1, the system is dynamic, a bunch of failures have happened, and then a new node arrived, and at time, T2, the system heals. It follows a bunch of protocols underneath, a bunch of multi-round protocols, and then comes to an agreement saying that, this is what the current state of the system, where nodes 76 and 64 have been reliably been detected as failed, and a new node 61 has arrived into the system. And Federation stops at that point. It comes and says, look, this is what I detect in the system. And then the other layers on top of it actually react to those failures. So obviously, I think in a real service fabric cluster, I will actually show it on the in the Service Fabric Explorer. Actually, a bunch of our own services, system-provided services, are also running in addition to this thing. There's a service called Failover Manager. It's a kind of like a system-defined or system-provided microservice, which itself is the one which is responsible for ensuring that all microservices are running in the system at the desired level of reliability. For example, if you wanted n copies of your stateless service to be running, it is the one which is making sure that those n copies are running. Similarly, when you say that you want n copies of your state to be maintained, it is the service that is actually maintaining those n copies. Obviously, there's a chicken and egg problem. It by itself, it's a microservice, but who is going to watch it? I think that's where the Federation, all these underlying protocols come in to make sure that this guy himself is running reliably. So that's why this problem, the system is self-sufficient, and that's why these underlying protocols and other things come together to make sure that the system gives you these kinds of reliabilities. And then the next level of service, another service that is responsible for taking care of the lifecycle management operations in the system is called Cluster Manager. It is the one which is giving you this ability to go and patch and upgrade your respective microservices. Remember, I talked about when a service, you want to resolve the name of a microservice and understand where exactly it is running and who is giving you that capability. That capability is coming from the naming microservice. There are multiple instances of that naming microservice because it's in the mainline code path. Every request that is coming into the system is getting resolved to go and locate the corresponding microservice, which is supposed to go and ultimately honor that request. Similarly, when you upload a bunch of, you provision a bunch of microservices in the system ingests, the corresponding code and, config data packages, and then puts them into an internal microservice called image store, from which it actually goes and creates these microservices on demand. All these services is what I'm, is it?
7.
You can actually see, you can see that
yeah.
So here is the Failover Manager service, which I mentioned. Here is the Cluster Manager one, and here is the Image Store one. And you can see that they're all stateful. There are primaries and secondaries, which I'm going to talk about a little bit later. And then you can see that the naming is actually the naming service has 3 partitions in it. There is, and it's also a stateful service. In addition to providing name resolution, it also stores a bunch of metadata for properties, naming properties, and other things. So you can see that there are 3 partitions for that. So that's what I actually showed to you guys. And then, as I said, this is another place where you can see that the cluster that you see running on your development boxes is indeed the actual cluster. If you actually go underneath Azure DB and open it up, you will see these services running. Of course, they're running on different machines and they're spread all over the place. But you can actually see that by actually going to the single your development box, I can show to you that all these services are running. In this sense, once again, we are not giving you an emulator when you actually write code on your development box. We are actually giving you a real functioning cluster. And in that sense, you can actually rest easy that all the code that you write there is actually going to run, well when you deploy it on premises or in Azure. So the next one, I'm going to talk about the same microservice that we talked about, the visual object one, and I'm going to make it stateful. But before I actually make that service stateful, remember when we induced the failure, the microservice actually jumped around. The visual object jumped around. In order for it to not jump around, we need to remember its location. And we're going to make that a stateful microservice. But before I do that, I want to give you guys the motivation of why stateful services are very important. If you really think about building high performance, low latency services. We are all used to building these 3-tier architectures where people told us, hey, go and build a stateless front end. And put all the business logic in the corresponding stateless, mid-tier. Then we say, go and put, because you need to scale, partition your backend so that you can either provision a bunch of databases or even, for that matter, put them behind SANs, so that you can actually store all your hardened state in databases or some storage systems. Then we come back and say, but this system doesn't work in real life, and there are lots of failures. Things are failing, and I want some reliable communication between my front end and the mid tier. So you introduce what we call a queue. So you put a queue and say, okay, let me put get my communication between the front end and the mid tier reliable by putting by making all the messages go through a reliable queue. Then you say, I want to actually achieve reliable communication between my mid-tier components themselves. And then you put another queue for them. Then you say, oh, my databases, I'm going to my databases way too often, including for my reads and writes. Let me put a cache in front of it. And then you put a cache in front of it. Then you think, oh, how do I achieve transactional guarantees that I'm promising to my customers? And you start actually thinking, how is this system all coming together? What happens if some failures happen? So you start managing your own transactions. You build a whole bunch of goop around it. And then at the end of the day, you are not sure, I'm not sure, whether the system actually is transactionally consistent. Because maybe if some failures don't happen, it works. But if enough failures happen in the system, I will guarantee to you that the system will have lots of issues. And more importantly, because the system is built out of a large number of individual components, which by themselves are not tail tolerant. I'll describe what tail tolerance means. Let's assume that each one of these components have 99.99 reliability, the 4.9 reliability that you want. But if you put all of them together, because every request is going and touching every one of these things, and if you compose 3 of them, your reliability drops down to 99.7 or something like that. In other words, you really think that you have a 4.9 system, but by building your service in this way, you are actually dropping down because every request has to touch every one of them, or majority of them, and if you touch 3 of them, your reliability has dropped. So how do you build really low, when you go and type something, or when you're talking on the phone to Cortana, you really need the response to be fast. How do you build such services without actually complicated architecture? And how do you reason about those services? How do you make those services correct in the presence of lots of failures and lots of faults? That's where you need stateful microservices. And that's what the motivation for this slide is. So in the microservices world, your job is simple. You basically start off by saying, I may have a front end, which is terminating, my protocol request. In some cases, you may actually do not even need it, because, if you think carefully, the front end is only needed to redirect the request to a corresponding stateful microservice. In other words, you can actually completely avoid these hops, and some of our internal services actually do avoid these hops. But assume that you have a front end to terminate your internet-facing request. Maybe it's a web front end. And then you want to talk to your backend. Now, the world is very simple. Because it's stateful microservices, the request gets completely satisfied there. All your reads are local. You're no longer thinking about caches because you can read locally. You are given transactions the system comes with built-in transactions. Again, I recommend you guys to go to the programming model talk, which is at 1:30 this afternoon. And you can actually see how to write a stateful microservice. It's not that complicated because all the heavy lifting is being done by the system. The system is giving you these transactions with which you can update state in these stateful microservices. And you can go and think about your system much more holistically. You no longer have to worry about, is this correct? As long as the transactions and the underlying system, service fabric, is correct, I can guarantee to you that this system is correct from your perspective, from your service point, perspective. Obviously, service fabric has to deal with all sorts of complexity, distributed systems complexity, but that's its job. That's where we come in, and we solve those problems for the benefit of everybody, including our first parties as well as the third parties now. And once you have all the OLTP part of your request, the request comes straight through the system, gets serviced, and returned. And so your OLTP part is very, very fast. It has the lowest latency, highest possible throughput. And then you can actually dump periodically this data into analytic engines, where you can run them through append-only stores and do a bunch of map-reduce jobs and other things. And, get insight into what's happening in your service. And in fact, those back-end systems themselves may be built using Service Fabric, but that's an immaterial thing from an architectural point of view. So really, if you go and think about any internet-scale service, this is how they are built. And this is how we are expecting you guys to build your services in the enterprise so that the enterprise grade really starts to make more sense than just calling it enterprise grade. Because enterprise grade means it's at the scale of whatever you can depend on. Today, we depend on a whole bunch of stuff, whether we are using phone, whether we're using tablets, whether we are using PCs at work. We get to depend on the availability of these services, and they actually are very delightful to use because they give you the best possible performance and lowest possible latency. So with that, we'll take the same visual object. This time, we made it stateful, and then, I have to put on my glasses, but, let's induce some failures and see what happens in the system.
Right, so this one, the 8506, if you noticed previously, the port number, this one was the stateless microservice. This is a stateful microservice, and as you can see, again, it has one partition, but it has 3 replicas. The primary is running on node 7, and there are 2 active secondaries on node 5 and node 3. So I'm going to put this pane to refresh to see the failovers happening. Then I'm going to go ahead and stop node 7. You'll see so previously, if you notice, the object jumped around in the space. This time you will see that as the switchover happens, a new primary is elected and the object is started from the same place because it hasn't lost the state. And you can also see that the replica is down, and then Gopal will talk in a bit in terms of how do we do replicated state machine, and you will understand that you only need a quorum of replica to be alive for us to make progress. So he'll show that in the next few set of slides. So
actually, I think it might be a good idea for us to really restart the node back.
Okay.
So basically, you can see that we are not. The machine is down, and the stateless service continues to run. And you can see the stateful service continues to run. And you can see that when the down replica comes back up, it would actually go through a series of transitions. Now it's down. It's become standby, and now it became ready. The state of that thing actually came back up. So in other words, I mean, I'm going to go walk you guys through the next set of slides of how this state actually is maintained by the system using what we call replicated state machines. And the system continued to run despite failures. And it is actually a persisted service. That's the key thing. I know it dealt with machine failures, and when the machine came back up, maybe because it got patched with an OS update, it came back up and the system continued to run. So the way you build stateful microservices is by building what we in computer science call replicated state machines. So we basically maintain a replica set for to back every stateful microservice, and we ensure that all those replicas remain consistent. In other words, the mutations that you apply to that state are applied in the same order by all replicas. That's what we call linearized order. And we actually already showed to you guys that we support read-write quorums. When one machine went down, we downshifted to 2 replicas because we can continue to run with 2 replicas. And when the second machine, when the down machine came back up, we again went back to 3 replicas. So you can see that the system is self-adjusting itself and making sure that the stateful microservice remains alive or remains available all the time, and the system is able to deal with failures. And here is, obviously, we showed to you guys, one stateful microservice, but if you actually go and look in the system, there's a whole bunch of them running. If you go and actually take a look underneath Azure databases, you will see millions of databases. We talk about 1.4 million databases on tens of thousands of machines, and each one of them is a replicated state machine. In other words, the system is individually tracking every one of those 1.4 million databases to make sure that every one of those databases are individually failing over, are individually available. So the system is working hard, not just at the machine level, but at each individual microservice level to guarantee to provide the guarantees that you really deserve for building your code and your logic so that you do not have to worry about these problems for yourself. So this is how the system actually looks underneath. I'm going to a little bit of a peek underneath this. So when a read comes to the primary, the read gets serviced immediately. So the reads are super fast. This is how I said, there are no caches in the system because the code is right next to you. I mean, the state is right next to you. You just read the state and return back. And then when a write comes through the system, it gets replicated to all its secondaries. And when a quorum of those guys acknowledge back, that transaction commits on the primary, and the primary can acknowledge back to its client saying that, hey, I honored whatever you wanted me to do. And then if a secondary, acknowledges a little later because maybe it was under load, the system will recognize that that particular transaction has already committed, and it will understand that, even the last secondary has committed this transaction. So what happens? This one actually shows a bunch of failures that can, the replicated state machine can go through. Basically, the primary has failed, which is what we have actually showed. When a primary has failed, you guys have actually seen in action on your development box how a secondary got promoted to become the primary. Then you also have seen how, the system, in this case, we didn't bring down another secondary, but if a secondary fails in the system will react and say, oh, the secondary failed, let me downshift all the way to 3. I mean, in this particular case, the replication factor that you really wanted is 5, but the system is operating temporarily at replication factor 3. And then the failed primary comes back up, which we have actually shown to you, and then it becomes part of the replica set by having the old new primary catch up all the transactions that the failed primary missed, and then actually bring it back alive into the system. Now we are back to running at a replication factor of 4. And a bunch of timers pass, and what we call replica restart wait duration, if you go and read the documentation of Service Fabric, and if that timer passes, the system says, okay, this particular secondary that actually died, maybe it took a really hard fault, and I should stop waiting for it to come back up. And it builds a new secondary on the side, catches, builds that guy, and when he's fairly caught up, he brings him back into the system for bringing the replication factor back to 5. So this is how the system is constantly watching every one of these stateful microservices and making sure that all of them are running at the desired level of reliability that we all want them to run. And once again, at nowhere in this conversation did we talk about machines. We only talk about microservices, how many instances of microservice you really want to have, what is the, how do you commit your code, how do you commit your transactions. Nowhere did you talk about machines, what happens, you say how many replicas you want, how many instances of microservice you want. You're only talking at the app level. This is what microservices-based architecture gives you. And this is where the power of the platforms like this come into play. Obviously, there is a, you guys also have seen how the system goes through a bunch of things like idle secondaries, active secondaries, primary, and all of these things. These failures can happen multiple times. While the system is failing, another set of failures can happen, and so it must be safe during all of them. So this particular slide shows how the system places a bunch of microservices, in this case, partitioned microservices in the system. So when the first partition gets placed, it places the primaries and secondaries on a set of machines. Second one, third one, fourth one, and fifth one. So, the system is ensuring that all the machines that are in the cluster are equally loaded in terms of, primaries and secondaries, so that the system is running most efficiently. This is where the cost, you want to run on the least number of machines that are necessary for making sure that your system is running at the desired degree of reliability and has enough of a headroom. So how many times have you gone into, enterprise data centers where machines are underutilized? They're running at 10% CPU. In fact, the entire virtualization came into existence because, a whole bunch of machines were underutilized. So here we are, trying to right-size the cluster. The system tries to right-size itself, saying that, my workload is asking me to say that I need 10 copies of this stateless microservice and 20 copies of my stateful microservice to run, 20 different types of stateful microservices to run. And I distributed them, and I have these machines which are underutilized. It may say that the entire cluster is running at a lower utilization than, let's say, 30% utilization. It can give up some machines. And then when demand arises, it can add new machines. You, as an author of your code, never bothered to actually think about how many machines I'm running in. The system is self-adjusting itself so that it gives you the benefit of running at the right kind of efficiency in the data center. So in this particular case, we have kind of shown to you what happens when a failover happens. Lots of machines are running in the cluster. What the system does is that it detects that failure using the federation subsystem, heals that failure, and then goes and notices that I want to go back and show that the green microservice had a failed primary on that box. Remember, primaries are very important replicas for a stateful microservice. So it goes and reacts faster for replacing those primaries with, remember, with a new primary. Remember, it picked a primary in a different machine. Then it goes and tells, if you go and look at the red one and the orange one, they're sending these replication operations which are not going anywhere. They're basically going into ether. And it goes and tells them, hey, don't stop actually sending replication messages to the dead machine. The system is now running perfectly fine, but it's running with a little bit of a lower replication factor. So the replica restart wait durations kick in, and it starts building new replicas, and we are back to now running at the desired capacity. With this, we'll show you how the same thing running in the cluster monitor. The cluster monitor will show you what exactly I showed in this particular slide, running on your dev boxes. It is 7. You can see that it is showing you what exactly I showed to you guys. What are the primaries, where are the secondaries.
And so I'll go ahead and turn off maybe say node 9, and then you'll see what happens to those replicas. So you can see here that for this primary, here are the secondaries. For this primary, these two are the secondary. So the system will react. All of these replicas are down. And for this, it already elected a new primary, which is here. And all of these replicas are marked as down. So the system reacted to this failure and then basically readjusted to make sure that the availability is there.
Yeah, we restarted back.
So as the node is started, those replicas will go through the transition of being standby, inbuilt, and then go back into. So you'll see some of them actually. So it happens fairly fast. And then some of them went to yellow, which was an inbuilt phase. We caught up those replicas to the missing operations that were happening while they were down, and then they again become ready. Once we come back to this slide, you'll notice here there are no primaries. Once we come back to this after a while, you'll see that system will also load balance the primaries in the system. So after a few, maybe after a few slides, when we go to the next demo, you'll see the system balance itself.
You can see that this is how this is really happening. This happens all the time in Service Fabric clusters, for different workloads. As I said, that they're Cortana, whether it is Azure databases or DocumentDB, a whole bunch of first-party services are all built on top of this, and this is what is happening. So with that, I'm actually going to talk to you guys about the life cycle aspects of our service. Remember that I showed to you guys the code running reliably. Now I will show to you guys how you can actually upgrade and patch this code. Remember, an application is nothing but, as I talked earlier, a set of microservices. There's a gateway microservice, stateless ones and stateful ones, and you put them all together, and you deploy them into the cluster. And when you deploy them, these pieces go into what we call the containers. I want to use the word container more generally than what people tell you. A container is nothing but a process group running inside maybe an isolation domain called container technology, whether it's Windows containers or Docker containers or Linux LXC containers. They basically are isolation domains, and the pieces of code that actually you run when we instantiate a microservice is the piece of code that you told the system to run. So you actually go and tell, I've implemented this microservice in this piece of code, and it is packaged as a set of exes or a set of processes. Like if you go and take a look underneath Azure database, the most important process that they launch is SQL Server.exe, the one that you actually see when you run SQL Server in your enterprise data centers. It's exactly the same piece of code that's running behind Azure databases as well. In addition, a whole bunch of other ancillary processes also run behind the scenes to support that process. For example, there is a watchdog process that actually is going and checking whether, check some errors are happening on that box, whether the database is still able to cope with the work that's coming at it. Or there's a full text indexing engine which actually is, indexing all the content that's going into the database so that your full text, contains, word, can be handled easily. So all of that stuff, supporting services, supporting exes, supporting processes, as well as the main process in which this microservice is implemented, are all running in the system, and they're all running in these process groups which are isolated inside containers. And now you can instantiate multiple copies of this code. For example, if you go and this is true in Azure database, the new Sterling databases that we are actually GA'd for you guys. Every database for every customer is running in a different set of processes so that each customer can actually go and upgrade their own database to a higher version of SQL and not affect other databases. In other words, you can have multiple instances of this application running so that you can do A/B testing. You can say, I want to upgrade my fast twitch application where all my bleeding edge customers are running, and keep the slow twitch application for my gold customers. You can do A/B testing, and this is how services are built in the real world. We deploy code, and we don't give the access. When we deploy the code, we first go and deploy them in pre-production clusters. We give them access to our bleeding edge customers, and when everything is looking great, then we go and upgrade the gold customers or protected customers' databases. That's how the system is built, and the system is giving you all those capabilities. So in the next slide, next demo, I'm going to show how the system actually performs these lifecycle operations. Obviously, the most important ones are making sure that you can provision and deploy microservices, you can upgrade them and patch them, you can monitor these microservices. So the system automatically rolls back. Suppose you deploy an application and then you want to patch it. And when you're doing the patch, something is going wrong in the system as the patch is rolling forward. The system detects that, oh, this particular patch is causing failures which I had not seen before, and it rolls it back. So it is doing this life cycle, it is giving you this very difficult to get capabilities that you do not get elsewhere. If you're starting with a bunch of machines, who is solving these problems for you? All of these problems are right in your face, and you have to really think about solving these problems. By depending on technologies like Service Fabric, which is what our internal services use, you get to actually get the same benefits and enjoy the same reliability that our internal services are gaining at the moment. I want to do one. So with that, I think we are going to show, I'm going to switch to 7. We are going to show the same visual objects, but this time, a whole bunch of them are running in the system. And notice that none of them are actually rotating. And I will show you the difference in code between the two versions. For the sake of time, here is the code which is different between the thing. Here, state.move is false. Remember, in version 1, it is false. If I go to F12 to that guy, you will see that at the end, there's a rotate. And it adds a 10-degree rotation if the rotate is true. Obviously, I think the default is false, but you've seen how it was. And in the V2 case, you can see that it is true. So that's the only difference between this code. Obviously, you may be deploying a bug fix, you may be deploying a new feature into the system, but from the point of view, you have a version 1 of the code and a version 2 of the code, and let the system actually go and deploy that, and Vipul will show you it walking.
So I've started the upgrade. You'll see that we're walking upgrade domain by upgrade domain, taking down the code, then putting the new bits there, and then the new bits, as Gopal explained, has the rotation. So you'll see some of those objects pause for a moment while they switch, and then once they come back up in the new code, they'll start rotating. So we'll see some of the objects start rotating as their primary switch over. So you'll see this blue object here is started rotating. And so basically, the system will go through upgrade by upgrade domain, and then make sure that the code that you are deploying is healthy. In this case, the code is healthy, and so it will continue to do the upgrade. If there was an issue, it would roll back. So it looks like we have one upgrade domain is completed. You can see the code going down on the second upgrade domain on the 3 nodes. So I have 3 upgrade domains, and there are 3 nodes in each of the upgrade domains.
So let me explain. I think that there's a notion of an upgrade domain and a failure domain. A failure domain is like a rack or a machine. If you put all your replicas on the same rack, if the rack dies, then you lost all your replicas. An upgrade domain is how you deploy your pieces of code, which I think if you're familiar with Azure terminology, that's what we use. So the system, when it's placing replicas, it ensures that it spans those upgrade domains and fault domains, so that no one deployment will kill all those replicas, or any given hardware failure, a top of the rack switch failure is not going to bring down all those things. And as you can see that it is proceeding cautiously, bringing down a bunch of upgrade domains, making sure that the system is remaining healthy. It goes and does a bunch of health checks, quorum checks, and making sure that the services are up and running, and then proceeds to the next one. And then when it's completely done, you will see that all of them are rotating, and looks like it is completely done. And all the visual objects are now rotating. You can see that this is almost close to impossible if you start from bare metal. You have to solve these problems yourself, and the way we do that is by taking maintenance windows, if you built it in a traditional way. But if you built it as a set of microservices which can be upgraded independently, which get their reliability using distributed systems technology, smart software over dumb hardware, you get all these benefits, which is what these big companies out there, internet companies out there, are actually building on. Of course, they don't make these kinds of technologies available, but we, as our, as Satya says, we are trying to make you guys realize the full potential in the enterprises, and we are making these kinds of technologies available to you to work on, to make your tier one enterprise applications become really tier one and run on commodity hardware and achieve unprecedented levels of reliability. This particular slide actually shows you, the same thing that you actually saw, walking, how the system walks different upgrade domains one at a time. And then with that, I'm actually going to showcase to you that we have what we call testability hooked into the system. Remember that you want the system to have failures all the time so that your code is actually getting exercised so that you don't go and really see the real failures or bugs in your system, in production system. So we have what we call a kiosk testability service, which is part of another one of those system services. And it goes behind the scenes and does bad things to the system. It goes and shuts down machines, kills replicas, and does a whole bunch of things, and ensures that the system continues to survive. And this is how we actually, this stuff runs in production as well, and this is how you actually make sure that the code that you're deploying to production is fairly well hardened or battle tested, because this system can, the chaos at the end of the day, what it's doing is that it is compressing a set of failures which you may see in a year into maybe a few days, and saying, can you survive those failures? And so, if you pass through these checks and have it run at a low grade all the time in production, you will be able to find the bugs sooner and yourself before your customer sees them. And you can see that, it's causing different kinds of failures. It's taking down nodes. It's taking down machines. Yeah. So with that, that brings me to the end of my talk. Basically, we have built this technology primarily for consumption by the first parties, and we as those first parties became successful, we decided to make it available to you guys. So we are excited about this moment because this technology is now finally seeing usage outside of Microsoft in some sense. The core of this technology has been in production for more than 5 years, but there are pieces of this technology that I think we are building. We started building a year ago, and we are continuing to build. The reason many of these first-party services use a bunch of low-level APIs in our system, but as we actually are making this technology publicly available, we are also exposing these APIs in easier to program, more approachable frameworks, and giving you the additional capabilities that are necessary for you to not really have to think about the underlying part. So we are making the system more and more approachable, and that's work in progress. We started on that work about a year ago, but the core of the system is baked, and this is where, and the layers above it, the sugary layers above it is where you may see some rough edges. And that's the reason we are actually cautious in giving to you guys these bits and making you go to the production. So what we request you guys is to go download the SDK, build your services, deploy them, run them, and we will take you to production by the end of this year. That's our hope. Because we will by then iron out all the rough edges based on the feedback that you guys have, so that at the end of this year, hopefully all of you guys are running on the same bedrock foundational technologies that we internally leverage within Microsoft. Thank you. If you have any questions, I'm happy to answer them.
Or are they two distinct workbenches from Microsoft for highly available?
Yeah, so I think the next 1.5, the talk at 1:30, will actually talk about the different programming models on top that you can use to build these stateful and stateless microservices. Okay. One of the ways you can build those stateful microservices is using what we call reliable actors. Okay. And a whole bunch of those concepts around that were borrowed by us actually leveraging the good work that Orleans team has done. In fact, if you had built an Orleans thing, you can actually more or less seamlessly migrate to this because the APIs will always, are very close to that.
Okay, interesting. Thank you.
Yeah, the question is, what are we using underneath the transport subsystem, right? So internally, as I have already said, that we don't have any need for reliable delivery of messages. We could have easily used UDP, but we do use TCP because we get two benefits out of it. One is fragmentation and reassembly. Because modern chips do a bunch of TCP offloads, checksum errors, and other things. So it is typically better these days to run TCP than UDP. Of course, there are special cases like broadcast and other cases where UDP is still more efficient and more is better for unreliable transport, which is what we depend on. WebSockets is typically a higher level protocol, which front ends use to go and terminate incoming requests, or keep a socket back to to send notifications back to the client. But internally, we use pure raw TCP.